back to lead a little bit. So I'm going to talk about some very basic principles of lead isotopes at first, followed by how we measure them, what are the materials and methods we're using, and in the end, I will give a few examples of applications of lead isotopes. And I think I can skip a few things at the start because we already heard some of these things. So we already know that lead has 4 main isotopes. We have 204, which is stable, and then 206, 207, 208, which are also stable, but also radiogenic, which means that the lead isotope composition of a system, the crust, for example, changes over time due to the radioactive decay of uranium and thorium, which form the radiogenic isotopes of lead. And the path along which our lead isotopes evolve depend on the mu value of a system or the uranium-lead ratio. At least in 206, 204 versus 207, 204 lead space. If we also look at 208, then of course thorium plays a role as thorium decays to 208 lead. But I will mainly focus on mu and 206, 204 versus 207, 204 because those are the most commonly used parameters in common or initial lead isotope studies. So in this systematic figure here on the right-hand side, we see a single-stage lead evolution model with the initial lead isotope composition of the system at the bottom left, which is often assumed to be the lead isotope composition of the Canyon Diablo turlite. And from our initial composition, our lead isotope ratios evolve along these curved paths depending on the mu value, which is represented by these 3 different colored lines. So assuming that we have a closed system which evolved from a single starting composition but contained phases with different mu values, which can be different minerals or different rock types or even different reservoirs, depends on the scale of the system we're looking at. If we analyze these phases today, the lead ratios will all plot along a straight line, which is nothing other than an isochron. And on the planetary scale, that would be the geochron, which is the solid black line in this figure here, and then we have paleogeochrons as the dashed lines. So we can use this information. If we have the initial lead isotope composition, we can use this information to track changes in magma source mu. Lead isotopes are commonly analyzed in minerals that do not contain any or only negligible amounts of uranium and thorium, like galena and K-feldspar, for example, as these minerals retain their lead isotopic composition from the time of crystallization. So unlike the whole rock system, for example, which whose lead isotopic composition is going to change over time due to radiogenic ingrowth, minerals like K-feldspar, for example, will capture the initial lead isotopic composition of their parent magma at the time of crystallization. So if we analyze whole rock, for example, and we want to get the initial lead isotope composition, we need to correct for the effect of radiogenic ingrowth first, which is possible if we have information on age and the uranium content, but it just adds another step to things that we need to do before we can get the initial composition of the system. As mentioned, once we have the initial composition of the magma, we can use that to distinguish magma sources that are differentiated to varying degrees, which is exemplified by the 2 white stars in this figure here, representing different mu values of the magma source. So this information, these isotopic signatures of lead, for example, in form of time-constrained isotopic maps, can give us information on processes that were involved in the formation of the crust and crustal architecture, for example. And this in turn can provide critical information on the formation and distribution or location of mineral systems, which is why there are currently two large-scale continent-wide lead isotope mapping projects underway in collaboration with Curtin. So there's one in Western Australia in collaboration with GSWA, where Mike Hartnady is the Curtin project lead. And then there's another one over east in collaboration with Geoscience Australia. And as I said, I will talk a little bit more about the applications later. But before I do that, I want to give a brief overview on the methods and also methodological advancements in the past few years. One of the most commonly, or at least traditionally, used methods for lead isotope analysis is TIMS, where samples are digested prior to analysis and then put through lead columns, which means that we purify lead from the matrix, which means that we don't have to worry about any interferences. We're also not really limited to any specific rock type, and we don't need a high lead content for TIMS analysis to be successful. In addition, of course, double spike TIMS is currently the method that offers the highest achievable precision. On the other hand, sample preparation is quite time consuming. The analysis itself is relatively slow, and of course, it's not an in situ technique. Then we also have laser ablation multi-collector ICP-MS, which offers a high spatial resolution down to 15 micron, or perhaps even smaller, but 15 micron is what we tested here at Curtin so far, and that worked well. That is a rapid technique. And as I mentioned a few slides ago, we can get the initial lead isotope composition from a magma by measuring lead isotopes in K-feldspar. And it's relatively easy to prepare grain mounts from K-feldspar, so we can do that in situ. And well, in addition, K-feldspar is a prevalent mineral in felsic rocks, making it very attractive for lead isotope studies, and then especially for these large-scale projects like the mapping projects I mentioned earlier. We do need a little bit of lead in K-feldspar for analysis using LI-ICP-MS to be successful, at least 10 to 20 ppm of lead, depending on the spot size that we use. And we also have to correct for the isobaric interference of 204 mercury on 204 lead, as we already heard about earlier today, which is a challenge, but it is a solvable one. So I guess in summary here, both of these methods have their strengths. And as always, the choice of analytical approach should rely on the scientific question you address to answer. Importantly, the results between both methods are consistent, which is shown in this figure here. So these are the results of the analysis of a new lead isotope reference K-feldspar called Albany. And we have TIMS analysis, and then the results of laser ablation multi-collector ICP-MS analysis at varying spot sizes, varying from 15 to 50 micron. And all of these analyses were undertaken here at Curtin. So as you can see, we have our TIMS results here as the white squares, and then the means of the laser results at different spot sizes as the colorful squares, and then the ellipses are 95% confidence intervals. So as you can see, they all agree very well. Another thing that this figure shows is the influence of the 204 uncertainty, that isobaric interference between 204 mercury and 204 lead. So even though we correct for that, we still commonly observe this linear scatter in our final results following that 204 trend, which is related to this interference. And this effect becomes stronger as we decrease spot size. But then again, with sufficiently high number of analysis, the means are all consistent. And I will talk you through the workflow of in situ K-feldspar lead analysis, because that's what I'm doing, and just to highlight a few advantages of this approach. So the samples we're using for K-feldspar in situ analysis go through a range of standard mineral separation steps, including separation by size, by magnetic property, and also by mass. And after these steps, the remaining light fraction, which is the fraction that contains the K-feldspar, if there is any K-feldspar in the sample, gets poured into a dump mount, which means that we end up with 1 mount per sample. We then use the TEMA to get a mineral phase map, and also at the same time a backscatter electron image, which then makes it super easy to identify our K-feldspar in the sample. And when we set our spots for in situ analysis, we can easily avoid things that could impair our analysis, like plagioclase, exsolution lamella, or inclusions, or cracks, etc. So once we're happy with that and we've set our spots, they're analyzed on the new plasma multi-collector in the geohistory facility here in the John Delator Center. And at least for the smaller spot sizes, all masses are analyzed on ion counters. And they include, of course, our lead isotopes, 202 mercury, which we need to correct for the isobaric interference on the 204 mass. And then also uranium, which is important, as I mentioned at the start. We're trying to get initial ratios, and we make the assumption that K-feldspar doesn't incorporate any uranium, and therefore lead ratios are not affected by radiogenic ingrowth. But this way, we can actually validate this assumption for every single grain, every single spot we analyze. The data reduction is then done using iolite, and some steps of data validation include, amongst others, assessing the uranium lead contents. So again, we're looking for no uranium and a good lead signal. We also monitor the magnitude of the mercury interference, because if we have relatively high mercury contents compared to lead, this can affect our correction, which is similar essentially as common lead in zircon. Okay, and that's the last part of my talk, applications. So I will talk about applications of lead isotopes in general, but the focus will be on applications of lead isotopes in K-feldspar. So the first example here for crustal evolution is from a recent study by Mike Hartnady and others, where they used lead isotope ratios in K-feldspar in Archean granites in the Pilbara to constrain the age and the nature of the precursors of these granites. So the colorful dots in this figure are the lead isotope ratios of K-feldspar. They're color-coded by crystallization age, which is also shown on the x-axis. And then we have in black the lead evolution of the bulk silicate earth. And then we have we have numerical models, or the results of numerical modeling here shown as dashed lines that model mixing with a Hadean crustal component and mixing with an Archean crustal component. So as you can see, based on these numerical modeling and the observed lead ratios, it seems unlikely that these rocks were influenced by a Hadean crustal precursor, which is opposed to what has been suggested in some previous studies. But instead, we can explain the observed lead ratios by mixing with an Archean crustal component. And I hope that I got this right. Cool. So moving on to crustal architecture. So I think I already mentioned that time-resolved isotopic maps can give us information on crustal domains and also the occurrence of metal deposits. And these are two examples here. On the left-hand side, we have a study from Andy Samitsa and others on lead isotopes across the Ida Fold and the Yilgarn Craton, where they show that lead isotopes track this crustal boundary. So in this figure, we have the Ida Fold in the center, and then we have lead isotopic signatures to the west and to the east of the Ida Fold. And as you can see, they're distinct, so they seem to track this crustal boundary. And then similarly here on the right-hand side, we have lead isoscapes from the Tasman element in Eastern Australia, where David Houston and others noticed that there is a correlation between gradients in mu value and the occurrence of base metal deposits. So gradients in mu value like here, for example, in the Lachlan origin, where we go from relatively low mu values to high mu values, and then these gray symbols in this map are base metal deposits. Lead isotopes can also track intracrustal differentiation. On the right-hand side, we have an example from a suite of granites in the Gawler Craton, the Tunkilia suite to be precise, where we have a correlation of unradiogenic lead isotope signatures or ratios with negative epsilon neodymium. So what this tells us is that the precursor was an older crustal component, but yet unradiogenic. So this has been interpreted to reflect a crustal component that became depleted in uranium during granulite fascist metamorphism. And then another example is here on the left-hand side from Helen Delavo and others, where we have lead isotope ratios of a K-feldspar sample from the Shat granite in the UK. And these distinct groups of lead isotope signatures observed in different crystal chips from the same K-feldspar sample have been interpreted to reflect isotopic zoning, which may be related to granite petrogenesis. So in summary, all of these examples that I've showed so far highlight that lead isotopes may record multiple overlapping signals of differentiation and fractionation, and they can provide complementary information to other isotopic systems like samarium, neodymium, lutetium, hafnium, etc. One last example I want to talk about, and I think we might hear about this in more detail later, is using lead isotopes as a provenance tool. Yeah. So this is going to be short because I thought that you would probably talk about it. Well, right. So we can, based on lead models, we can calculate model ages, lead model ages for K-feldspar, which means that if we have a model that works well for a certain region, this can provide some geochronologic information as well. And this study is from Eastern Greenland. And what we see in this figure are the age proportions of detrital K-feldspar and detrital zircon within the same sedimentary formations. So we have in blue Phanerozoic ages, orange Proterozoic, and then in pink Archean. And as you can see, the proportions between detrital feldspar and detrital zircon vary quite dramatically, which is related to K-feldspar being a lot less refractory than zircon. So K-feldspar tends to record first cycle processes, whereas zircon commonly, because it is so stable, commonly survives multiple cycles of erosion and deposition, which means that source to sink relationships can be blurred. So K-feldspar is provides an opportunity here to get additional information to zircon, which helps in provenance studies. And that is it